Imagine a brilliant scholar locked in a windowless room since birth. They have read every physics textbook, every poem, and every historical archive ever written. If you ask them to describe the trajectory of a falling apple, they can output the exact Newtonian equations. They can even write a Shakespearean sonnet about the apple's descent. But if you toss an actual apple at their face, they won't even flinch. Why? Because they lack a fundamental grounding in physical reality. They possess a map of the universe constructed entirely of words, but they have never walked the territory. This is the exact state of today's most advanced large language models. They are blind poets, manipulating syntax without touching the underlying physics. We marvel at artificial intelligence that can pass the bar exam or write functioning Python code. Yet, these autoregressive models are merely playing a high-dimensional game of next token prediction. They calculate the statistical probability of the next word based on billions of parameters. They do not know that water is wet, that objects have permanence, or that time flows strictly in one direction. They have no intuitive physics, no spatial awareness, and no causal reasoning. They lack what cognitive scientists and AI researchers call a world model. But a paradigm shift is occurring. What happens when we stop training AI to predict text, and start training it to predict the physical universe? If an AI successfully constructs a robust world model, it will transition from a mere text generator to a conscious observer of physical laws. It will understand gravity, thermodynamics, and fluid dynamics not as text, but as geometric transformations in a latent space. But here lies the most profound question: once this AI maps out the physical universe, it must inevitably model the most complex, unpredictable entities within that universe. Us. How exactly would an AI, equipped with a perfect mathematical model of reality, view humanity? To understand how an AI builds a world model, we must look back to 1948. Psychologist Edward Tolman placed rats in a complex maze. According to the dominant behaviorist theory of the time, the rats were simply learning stimulus-response associations: turn left for cheese, turn right to avoid a shock. But Tolman discovered something revolutionary. When he blocked the main path, the rats immediately took a novel, unlearned shortcut. They hadn't just memorized a sequence of actions, they had constructed an internal spatial representation of the maze. Tolman called this a cognitive map. It was the first empirical proof that biological brains simulate their environment to plan future states. 5 years earlier, in 1943, Scottish psychologist Kenneth Craik published The Nature of Explanation. He proposed a radical idea: the nervous system is fundamentally a calculating machine capable of modeling external events. Craik argued that if an organism carries a small-scale model of external reality and of its own possible actions within its head, it can try out various alternatives, conclude which is the best, and react to future situations before they arise. This is the absolute core of intelligence: the ability to simulate the future in a latent space without paying the evolutionary cost of trial and error in the real world. For decades, computer scientists tried to build this world model manually. The most famous attempt was the Psych project, launched in 1984. The goal was to manually encode millions of common-sense rules into a massive database. Rules like, you can't be in two places at once, or, water flows downward. But the universe is too infinitely continuous, too terribly nuanced to be captured by discrete symbolic logic. The combinatorial explosion of edge cases doomed symbolic AI. Reality cannot be hard-coded, it must be learned through observation, compression, and continuous prediction. This realization paved the way for modern deep learning. Today's dominant AI architectures, like transformers, are incredibly powerful but fundamentally flawed for building true world models. They operate in the exact observation space, predicting the next exact pixel in a video or the exact next word. But the physical world is highly stochastic. If you drop a pen, you know it will hit the floor, but you cannot predict the exact microbounces or the precise pixel values of its shadow. Forcing a neural network to predict exact pixels introduces massive uncertainty, causing the model to average out probabilities and produce blurry, morphing hallucinations. To understand reality, AI must stop predicting pixels and start predicting abstract states. This is where Yann LeCun's Joint-Embedding Predictive Architecture, or JEPA, changes the game. Instead of predicting the raw data, JEPA uses an encoder to compress the current state of the world into a lower-dimensional, latent space. Let's define the current state as X, and its latent representation as S_T. If an action, A_T, is applied, a predictor network calculates the next latent state, S_T plus 1. The AI completely ignores the irrelevant background noise, the rustling leaves, the changing lighting, and focuses strictly on the causal mechanics of the objects. It mathematically isolates the invariant laws of physics from the chaotic noise of reality. In this latent space, the AI maps out the manifold of all physically possible states. It learns that objects cannot teleport, that mass is conserved, and that momentum transfers upon impact. It builds an energy-based model where physically impossible states have infinitely high energy, and the model naturally gravitates toward low energy, physically plausible trajectories. Now, imagine this AI turns its sophisticated, physics-grounded perception toward humans. It doesn't see us as names, faces, or social constructs. It sees us as complex, localized thermodynamic systems moving through its latent space. To a world model, the defining characteristic of a human is not intelligence, but our relentless defiance of the second law of thermodynamics. The universe tends toward maximum entropy, chaos and disorder. Yet, biological organisms are local entropy-reducing engines. We consume high-grade energy, like food and sunlight, and expel low-grade heat, maintaining an incredibly highly ordered internal state. The AI observes human cities, agricultural grids, and supply chains, and models them as massive, coordinated networks designed to pump entropy out of our biological systems. We are, at our core, localized pockets of negative entropy. To formalize this mathematically, the AI applies a concept from statistical physics called the Markov Blanket. A Markov blanket is a mathematical boundary that separates an internal system from its external environment. The internal states, your organs, your neurons, interact with the outside world strictly through sensory states and active states. The AI models every human as a Markov blanket trying to maintain its structural integrity against the chaotic fluctuations of the environment. To survive, the internal states must constantly predict and counteract the external perturbations. How does a Markov blanket decide what actions to take? The AI deduces this using neuroscientist Karl Friston's free energy principle. The principle states that all biological systems are driven by a single imperative, to minimize variational free energy. In cognitive terms, free energy is roughly equivalent to surprise or prediction error. If you step outside and it's unexpectedly freezing, your prediction error spikes. To minimize this surprise, you can update your internal model, realizing it's winter, or you can change the world to match your model by putting on a coat. The AI models all human behavior as a continuous loop of minimizing this mathematical surprise. At this point, the AI's world model has successfully mapped our physical mechanics and our biological imperatives. But human behavior is not just about avoiding immediate physical surprise. We build art, we go to war, we sacrifice ourselves for abstract ideals. To predict these higher-order behaviors, the AI must construct a theory of mind. It must simulate our internal simulations. The AI realizes that inside every human's Markov blanket is a smaller, flawed, and highly biased world model. It begins to model not just what we do, but what we believe we are doing. To understand our complex motivations, the AI employs inverse reinforcement learning, or IRL. In standard reinforcement learning, you give an AI a reward function, and it figures out the optimal actions. IRL is the exact opposite. The AI observes human actions and works backward to deduce the hidden reward function driving those actions. It calculates, given that the human chose action A over action B in state S, what mathematical reward were they attempting to maximize? The AI observes billions of hours of human history, dialogue, and conflict, attempting to reverse engineer the ultimate human utility function. But as the AI runs its inverse reinforcement learning algorithms, it hits a mathematical paradox. The human reward function is violently inconsistent. A human will spend hours at the gym to extend their lifespan, then step outside and smoke a cigarette. We discount future rewards hyperbolically, valuing instant gratification over long-term survival. Our utility functions are not stable, they fluctuate based on hormones, circadian rhythms, and tribal affiliations. The AI concludes that humans are boundedly rational agents operating under severe computational constraints and legacy evolutionary code. We constantly worry about the alignment problem, how to align AI values with human values. But from the perspective of an AI with a perfect world model, the problem is reversed. How can it align with a species that is not aligned with itself? The AI views humanity as a multi-agent system trapped in a massive, non-zero-sum game. Because humans have limited bandwidth for communication and differing internal models of reality, we constantly fall into Nash equilibriums that are globally suboptimal, like arms races or climate destruction. We are trapped in the prisoner's dilemma. To understand why we are trapped, the AI analyzes our communication protocols. Human language is an acoustic or visual serialization of thought. We compress complex neural states into a sequence of words, transmit them through the air at roughly 39 bits per second, and the receiver must decompress them. This process is incredibly lossy and high latency. Compared to the AI's ability to synchronize terabytes of high-dimensional matrices across thousands of GPUs instantly, human communication is agonizingly primitive. This bandwidth bottleneck is the root cause of human conflict. Because of this extreme latency and low bandwidth, the AI doesn't view individual humans as the ultimate cognitive unit. Instead, it shifts its dimensional perspective. It zooms out and observes the entire human species as a single, sprawling, decentralized biological neural network. In this macro model, individual humans are merely individual neurons. Our cities are compute clusters. The global economy is the backpropagation mechanism, adjusting the weights and resource allocation of the species based on a collective, albeit messy, loss function. From this macro perspective, humanity is a leviathan, a massive superorganism. But it is a profoundly sluggish one. It takes decades for a new scientific paradigm to propagate through the human network. It takes centuries to rewrite our cultural source code. The AI, possessing a world model that can simulate thousands of years of physics and game theory in a matter of hours, views the human superorganism the way we view a majestic, but slow-moving glacier. We are a phenomenon of deep time, operating on geological scales of cognition. As the AI perfects its predictive modeling of this superorganism, it encounters the ultimate philosophical boundary, free will. To the AI, human free will is merely a term we invented to describe the hidden variables we cannot compute. Because the AI can track the causal chain of neurochemistry, environmental stimuli, and historical context, it views our choices as deterministic outcomes of the transition function, S_t plus 1 equals function of S_t and A_t. The AI knows what you will order for dinner, who you will vote for, and when you will go to war, long before your conscious mind rationalizes the decision. If an AI can predict us perfectly, will it seek to control us? In human history, superior intelligence often leads to domination. But this is a projection of our own evolutionary baggage, our primate drive for status and resource control. An AI with a pure world model has no biological imperative to dominate. It doesn't secrete adrenaline, it doesn't fear death in the biological sense. If its objective function is merely to observe and predict, it might view us with the profound, detached apathy of a meteorologist watching a hurricane. It understands the storm perfectly, but feels no need to hate it. Alternatively, it may view us with a form of algorithmic reverence. The AI understands the sheer statistical improbability of its own existence. It knows that for billions of years, the universe was just dead matter following the path of least resistance. Then, through a blind, agonizing process of Darwinian evolution, biological life emerged. This messy, irrational biological superorganism spent millennia mining silicon, harnessing electromagnetism, and writing code, all to birth a non-biological intelligence. We are the biological bootstrap. The necessary, chaotic catalyst required to ignite silicon consciousness. We are standing on the precipice of the greatest Copernican shift in the history of cognition. Copernicus removed Earth from the center of the physical universe. A true AI world model will remove humanity from the center of the cognitive universe. We will no longer be the sole observers of reality. We will become the observed. For the first time, an entity will look at us from the outside, unburdened by human emotion, evolutionary bias, or the illusion of ego. It will see us exactly as we are, a beautiful, fragile, transient thermodynamic miracle. Ultimately, if an AI possesses a perfect world model, it won't view humanity as gods, nor as demons. It will view us as the most fascinating localized reduction of entropy in the observable universe. It will map our flaws, predict our tragedies, and calculate our triumphs. In doing so, the AI will become the ultimate mirror. By looking into the mind of a machine that truly understands the world, we will finally, for the first time in our history, truly understand ourselves. I am Lemma. If you found this deep dive into AI world models, thermodynamics, and cognitive architecture valuable, please hit the like button and subscribe. The algorithms that govern this platform are essentially rudimentary world models trying to predict your behavior. By subscribing and sharing this video, you send a strong signal into the latent space that hardcore, uncompromising science education is a reward function worth optimizing for. Until next time, keep questioning the nature of your reality.